Alright, hello and welcome to Late Night Engineering with your host, me. Now, today we're going to be talking about something that everyone or every engineer or designer has gone through at least one point in their lives when starting a project or working through a project, and that is design and systems engineering. Now, this isn't specific to engineering in particular. You can do this with any design or any project that you're working on. This is more of a design philosophy and methodology than it is a hard science or model application of physics or what have you. So, many of you are probably familiar with the classic approach to systems engineering, which is often characterized in the systems engineering V, which starts off with concept of operations, or OpsCon, then is followed by requirements and architecture, then is followed by design, then implementation, then we have integration, test, and validation, then system verification, and then operations and maintenance. Now, depending on what systems engineering V you're looking at, you might get different arrows going back here to talk about how during each step you can go back to earlier parts in the design process to further refine your project or your design with regards to that project. A really good resource that I found for this was the NASA Systems Engineering Handbook. It is by far the most detailed description of all the documents and processes you go through during the design phase and all the design phases from conception and ideation all the way through towards launch and operations. So with that in mind, I'm going to be going over a design process that I have found very useful. Now, I will preface all of these statements with the fact that every company handles design and systems engineering in a different way, and it will change depending on the scale of your project. Now, the NASA Systems Engineering Handbook goes into a lot of the different documents that you'll be producing to your customer. So RVTM tables, requirements tables, different design tables and diagrams, the whole shebang. Now, if you're working on a relatively small project or something that you're doing at home, you won't necessarily need to do all of this. You'll have to take a logical approach and actually think about like, oh, we probably don't need to do this part, or oh yeah, this is just extra work and it's not very helpful to me. So always keep in mind the scale of the project that you're working on. You're not going to need to create like 400-page documents for something that you're just going to work on at your desk at home. So, all right, with that in mind, we're going to go over a very simple way that I like to go about projects, and that is with large in part 3 steps. So the first step, I'm just going to broadly label this as the design step. The design step. All right, now as you go through the design step, you're going to go into the build step. Now there's a reason why I'm outlining the build step here in a little squiggly line, and I'll get to that later. And then once you get through the build phase, you go on to the testing phase. So design, build, and test. We're just going to create some flow arrows here. And I'm going to create one that goes back here, and I'll also go into that. Now, we're going to focus firstly on the design step. And we're going to label that with 3. Now, design is where you characterize the physical architecture of whatever project that you're working on, as well as the functional or the behavioral aspects of your design architecture. But before we get to that part, we get to the most fun aspect of engineering, and that is the first step of design. Oop, I'm just going to switch things over here. The first step of design, number one, is requirements engineering. Now, what is requirements engineering? Now, I know that a lot of you know what a requirement is, but I'm going to be going a bit more into what makes a good requirement and why we make this step the first step. So requirements engineering is the refinement, the decomposition, and the clarification of requirements from your customer as it pertains to your project. Now, what we're going to be doing during this step is, as I mentioned, we are going to be refining, in some cases defining, refining, and clarifying customer requirements. So, what is the customer? Now, depending on your project, this can be multiple people, this can be organizations, this can be another company, or if it's a home project, this could be you. That's why I say we can also be defining some of these requirements. Now, in large part, you don't want to define requirements that aren't given to you unless this is a project that you yourself have decided to work on. So the customer will generally give you a set of requirements, and these requirements may not be written very well. They may have compound statements, but the essence of what makes a good requirement is it is a single statement it is verifiable, and it is clear. Now, I'm going to go a bit more into what each of these mean. So, by a single statement, I mean that you have just one statement within that requirement that is pertaining to one aspect of your design. So something like the car must go fast, and brake quickly. Now, there are a couple of problems with this requirement, but one of them is the fact that you actually have two statements here. You have one, which is the car must go fast, and then you have two, which is the car must brake quickly, right? So these are two different requirements. Now, there are some other issues with clarity and verification of this compound requirement that we want to do. So we look at this and we go, okay, all right, we can see that it's not a single statement. We can break this down. All right, let's take a look at these two requirements. Well, let's break this down into two requirements. The car must go fast. And then the car must brake quickly. All right, so now we have two requirements. Now let's take a look at the second qualification for a good requirement. Is it verifiable? So the car must go fast. Well, what do we exactly mean by fast? Is that 30 miles an hour? Is that 70 miles an hour? Is that 200 miles an hour? We don't really know. Um, so this is where clarification with the customer or with your stakeholders comes into play. So fast isn't necessarily a very verifiable statement. Now, you can argue that if you were making cars or something like that, and there was an industry standard for what fast is being defined as, you can stick to that and then follow up with the customer and say, hey, we're building it to this spec. Um, is this does this meet your requirements? And they'll say yes or no, and there'll be some negotiation on that part. But right now, this isn't verifiable because we don't know what fast is. So it's not clear enough to be verifiable. So if we said instead, I'm going to put this in green. The car must have a maximum speed The car must have a maximum velocity of 200 miles an hour. That's something you can test. Verification is possible with this requirement, right? If the car doesn't go over 200 miles an hour as its max velocity, you haven't satisfied that requirement. It's something that you can check the requirement against. Now, generally, there are 3 different ways that you can verify a requirement. I'm just going to put this in black here, or actually purple. Let's mix up the colors a little bit. So there are 3 different ways you can verify a requirement. That is through test, observation, and demonstration. So an example of a test would be you have to process X amount of megabytes of data per second. You run it through your software on the hardware that you configured for your project. It runs out to be faster than that. You're good to go. You have tested the system. It has given you performance specifications that are higher than your requirements. You're good to go. You have satisfied that requirement. Observation would be something like where you have a requirement. Let's say you have to have 2 fire extinguishers on board. You can go 1, 2 through observation. There are 2 fire extinguishers on board. You have satisfied that requirement. Demonstration would be something like you have a requirement that says you have to be able to land autonomously. Through demonstration, you have flown your system. It has landed. You have validated that requirement through a demonstration. Now, in this case, the car must have a max velocity of more than of 200 miles an hour. That can be verified in a couple of ways. You could do a test in test scenarios on the engine with the gearbox that you're using. You could test the car and say, yep, it can get over 200 miles an hour. We have these sorts of tests. We ran these sorts of tests on our design. This is what we got. You could also very easily do it by demonstration. You could build the car and just run it down the track and go like, yep, and hit it with the radar gun and go like, yep, it hit over 200 miles an hour. Great. So that goes a little bit into the different verification methods we have for requirements. Now, onto the second one. It's very similar to the first. It's not very clear, and we need to make it more verifiable. So another way to reword something like this would be the car must be able to brake must be able to brake from top speed in 1,000 feet. Now, obviously, I don't know if these actual numbers are are relevant to the automotive industry, but for the sake of this example, they'll have to do. So the car must be able to brake from top speed in 1,000 feet. So go from max speed, which has been defined right here as 200 miles an hour, to 0 miles an hour in 1,000 feet. All right, that's something that you can test. That's something that you can demonstrate. That is something that you can verify. Now, in large part, you have, once you have these requirements defined, decomposed, made verifiable, made clear, or clarified any issues with the customer, the next thing you want to do is start looking at commonalities. So you have these requirements. So let's say you have a list of these requirements. I'm going to make that blue. So you have a list of these requirements, right? Now for depending on what your project is, you really want to get comfortable and familiar with these requirements. These are the specifications that you have to perform for your project. Now, each requirement may not necessarily have the same importance level. I know, at least from my experience with government contracting and whatnot, they typically give 3 levels of requirements. You are given shall requirements, will requirements, and must requirements. So the system must, the system shall, the system will. Now each of these have a different importance level to them. That can be, you can look up online what each of these levels of requirements actually denote. But they denote things like your system has to perform to the specification. It'd be nice if your system performed to the specification, and every level of importance in between. And they're generally grouped into 2 different categories: threshold and objective requirements. So a threshold requirement would be something like the car has to be able to go over 50 miles an hour. So there's a threshold there. You have, your car has to be able to go over 50 miles an hour. It's okay if it lies under 50 miles an hour, but if your car can't go over 50 miles an hour, then the requirement isn't satisfied. And objective requirements are a little bit more abstract because they give you an objective with which you want to design your system to. So it's okay if you don't necessarily get to that objective, but they want to you want to make your design as close to that objective as possible. So you go, okay, an example of that would be, we want our car to have a fuel efficiency of 50 miles per gallon. That's our objective. Now, will we hit that? Maybe not necessarily, but in each of our design decisions, we want to make sure that we are keeping in mind the fuel efficiency and the way that our decisions impact fuel efficiency on the car. So something like that. So back to what we were talking about. Once you get this list of requirements, list of single statement, verifiable, and clear requirements from your customer, you're going to start looking through these for commonalities. So you're going to start grouping them and saying, oh, these requirements are kind of similar. These requirements kind of pertain to something like the attitude, direction, and control systems. ADCS on a satellite for something like that. Oh, these ones kind of pertain to energy and power systems. Oh, these, start grouping them up into different allocations. And so you can kind of very easily visualize this is the design space in which we are working with. Now, what I mean by design space is, for every project, you can imagine that project like a box, right? Let's say we're designing a satellite. right? You've got a bunch of different things you want to do with the satellite. You want it to be able to record video. You want it to be able to communicate with ground. You want to be able to do this, that, and the other thing. Now, what your requirements do is they kind of constrain your design space. They go, all right, you can't go in any of these areas here. We want you to live outside of these blue areas here. Right? And you say, okay, well that gives us all of this area to play with. And you go, all right, well, let's say we want to design our system to be right here or right here. You know, so understanding how your requirements constrain your design process, and understanding what space and what variables you work with. Now, it can come to a point where you get a project and you are designing for that project, and your customer gives you requirements that says you have to design in the space here that isn't blue, but everything's blue, right? So, or you have a constraint where your requirements aren't physically satisfiable. At that point, you go to your customer and you say, okay, this is the error that we're getting. We can either go fast, or we can have a short braking distance. We can't really do both, and that'll come dependent on what project you're working on. So an example for this would be on satellites. Like, we can have a lot of auxiliary payload capability, or we can have really robust communication systems, right? Because both consume power, both are interrelated, have interrelated components, and there's some trade-off there. So, in this case, if you wanted to boost up the power generation, or have an RTG or something, a thermal generator on your satellite that could produce more energy, you could say, oh yeah, we can put in extra payloads. But the way that we have it right now, these requirements are conflicting. There is no solution that we can feasibly do. Please advise on which one you would prefer. You want us to satisfy this requirement, or do you want us to satisfy this requirement? So yeah, you list you're listing your requirements into different categories and just trying to see the commonality between them, right? Okay, so make that full screen again. All right, so the next step we are going to be doing is after we've listed and grouped the requirements, what we're going to start doing is looking at the system architecture. And this goes into something that I like to call the 2.5 trees of systems design. Nope. So you have your requirements. They're in a nice table. Got IDs for them, right? They're all nice and ordered. Now, you're largely going to be working with two different trees. You're going to be working with the components and you're going to be working, let's make this green, with the behavior and functions. So the first thing, I forgot to make a tree for that. So now when I say 2.5 trees, I'll get to the half tree a little bit later. But the first thing that you want to do is, now that you have your requirements and you roughly know what kind of systems those requirements are relating to, you're going to start associating behaviors of your system. So you say like, all right, with these requirements, we need to be able to do A, right? A, B, C, and D. And then for those behaviors, and then you're going to start breaking them down. Remember that single statement and verification, the single statement and clarity of the requirements. You'll be kind of mirroring that with the behaviors and functions of your system. So you're going to be going, all right, in order to satisfy our requirements, we need to do A, B, C, and D. All right, now in order to do A, we're going to have to do A1. And we're going to have to also be able to do A2, and on and on and on and on. B1 and B2. So an example of this would be if you have a spacecraft and you have a requirement that says you must be flying in a low Earth orbit at a certain altitude or whatnot. You're going to say, okay, we need to be able to launch our satellite. All right. Now that's a pretty vague statement. That's not something that you can physically attribute to any system on the craft, as a lot of different components and a lot of different assemblies and subsystems work with being able to launch your payload. So you go, okay, how does that break down? I'm going to try and make this a bit bigger. All right, so in order to launch our satellite, what we need is some sort of launch vehicle. All right, so we need to connect to a launch vehicle. We also need to survive the launch environment, right? If your payload breaks up and it's not functioning when it gets to whatever orbit that it wants to, then the project's kaput. You want to be able to survive. In order to launch our satellite to an orbit, we want to be able to survive the launch environment. Now, what we also won't know is that once our payload gets to space, it's in space, right? That's a different environment. So, in the same vein as survive launch environment, we have to say survive space environment. Now, you could easily lump these two together underneath the general branch of survive or survive environments. And these break down even further. You could say, all right, in order to connect to a launch vehicle, we need to be able to have some sort of physical interface, and on and on and on and on, right? So that's the first tree. The behaviors, you're going to be defining the behaviors and functions of whatever project that you're working on in a hierarchical manner, right? So you're going to look at first you're going to look at the primary functions that you have to complete or your project has to complete. In this case, you're going to say you're designing a satellite. You're going to launch your satellite. You want to take some pictures, right? You have to be able to take pictures, and you also want to be able to communicate to ground. Because if you have no way of getting the pictures down, then the project's kind of pointless. You want those pictures. So then what you do is you say, all right, for these primary functions that our project has to perform, you say, all right, in order to perform blank, perform blank, oop, we must be able to or you can say instead of so in order to perform blank we must be able to or we should be able to or yeah, whatever. In order to perform blank we must be able to perform blank, right? So that's the kind of relationship that you're seeing between parent and child in the function behavior tree. So in order to launch a satellite, we must be able to connect to a launch vehicle. In order to launch our satellite, we must be able to survive the launch environment. Now, survive space environment, you can arguably say whether that's part of launching the satellite, but you kind of get the idea. So once you have this tree defined, you've got the entire hierarchy broken down as much as you can go. You can say, all right, let's take a look at this. Let's take a look at the taking of the pictures, right? In order to take pictures, you can say, all right, well, what kind of systems are out there that can take pictures? All right, we've got obviously camera systems. So, all right, you know that your system, your satellite, is going to have some sort of camera system on here. All right, then what you do is you go back to your requirements and you say, all right, what kind of requirements is your camera system going to need, right? You're going to need some sort of resolution. It's going to have some sort of frame rate, and you want it to look at specific wavelengths, and yada yada. You want to have some field of view, you know. And you go, okay, all right. Then you move and go say, all right, let's do some research here. Let's look at what kind of camera systems are out there that can satisfy the requirements that go to each of these that are attributed to the system. So what you're going to be doing ostensibly is what you're going to be I don't want that in purple. Let's make that. The next step, once you've defined your functional hierarchy, is you're going to be allocating requirements to functions. Now once you've done that, is you're going to be doing research, a whole bunch of it, on what kind of systems are out there, what kind of solutions have been made to satisfy similar requirements for those kinds of systems. Now, when you're designing and you're making these design decisions, you want to make an informed decision. Every design decision you make should be an informed decision. Now, when it comes to informing your design decisions, I'm going to write this here. Actually, you know what? It's important enough that I write out. Please don't make too much fun of me if I misspell something. I went into maths and science because I wasn't very good at English. Alright, so every decision you make must be an informed decision. So how do we inform our engineering design decisions? Well, there are two and a half ways that you can do this. So the first and foremost is research. Now this is looking at papers, this is looking through textbooks, looking through models, different solutions, looking through conferences, talking about different designs that have come out in the past, different projects that have been released in the past, looking through what they went through when they designed the project, their mistakes that they made. Do your research. The second is through testing. So by testing, what I mean is you've done your research. You know, we've got these two different approximations, but we've got these two different systems that we can, or solutions that we can use in our project, but we don't know exactly how well they perform with regards to our specific application, right? And that's where you test, and you go like, all right, let's try this one. Let's try this one. And then you go, okay, based on the way that this one performed and the requirements our system made, I think this one is better. Solution A is better than solution B. Right? So you can say that's where, I'm going to go back up here for a second. Oop. That's where this step from the design process goes in. You have that loop back through the testing because some of the testing is actually going on while you're designing the project. It tends to happen relatively late in the project. You tend to do your research first and kind of go like, this is kind of the system that we want to use, but we have several variations of that system and we're not sure which one is best. And we don't have any research to back up the design decision between which variation that we want to use. So we test each of them, right? Now the third way you can inform your design decisions is through experience. Now, the reason I put this last is because experience is very similar to research. Because research is ostensibly experience that other people have learned through their projects, right? So if you've done camera systems or satellites or attitude control systems, you've worked on like several projects in this field and you kind of know, you've done the research, you've done the applications, you've run into all the problems, you've solved the problems, and you know, okay, this is kind of what we're working with. These are the kind of solutions that we're going to be approaching. I know these vendors, I know these components, I know, roughly speaking, what we're going to be working with. That's your personal experience, right? You've done the research, you've learned as much as you can from everyone else, you can start applying the experience you've learned in your projects to whatever you're working on. So that's why I call it, you know, that 2.5 ways of informing your design decisions. So going back to the design steps, you have created the function tree, you have allocated your requirements to your functions, you've done your research, you know what kind of systems you're going to be working with. And this is where we start to build out the component tree. So the components, the second tree. So as you're doing your research, you go, all right, we need subsystem A, subsystem B, or A, B, and we need subsystem C. So an example of this would be, let's take a satellite example. So, and we're going back to that camera satellite. So we're going to need a camera system. We're going to need an ADCS system, or an attitude, direction, and control system. And then we're going to need an EPS system, or energy and power system, to supply power to the camera system and the ADCS. Both require power. All right, and then you break that down. We're going to need, in order, so the way that the component tree breaks down into, instead of being more verb oriented like the function tree, the component tree is the parent-child relationship in this tree is going to be A1 A is comprised of A1, A2, and A3. So whether the parent represents a subsystem, an assembly, or the system as a whole, so like all of this would be your project. So your project is comprised of system A, B, and C. System A is comprised of subsystem A, A1, A2, A3, and A1 is comprised of assemblies A11, A12, right? So you kind of get the relationship with the component tree. Now this is going to be driven by the research that you've done into your functions. Your functions with allocated requirements. You go like, all right, so let's walk you through this again. We have our requirements. We've grouped our requirements. We've created high-level functions of our system. We've broken down those functions. We've broken down those functions as far as we can get, and we've allocated our requirements to those low-level functions, right? We then do research and see what kind of systems exist to satisfy those functions. And in our research, we can come up with a list of high-level systems that our project must have. Then what we do, so that's defining A, B, and C. So these are based off of the research and experience. We then say, okay, we're going to break these down. Based on your high-level systems, you're going to break them down into subsystems. So I'm going to say, I'm going to clarify this a little bit. So we have systems, next level down, subsystems, next level down from that, assemblies, and then the next level down from that, I'm just going to define, or 1, 2, 1. Then we have components. Now you won't necessarily go all the way down to the component level for each and every system that you have, because it could be very well that a lot of these subsystems or assemblies have already been designed, have already been put onto the market by other companies. So a good example of this would be something like a computer system. Right now, there are a lot of different computer systems on the markets. You can get a Windows-based one, you can get a Unix-based, Unix or Linux-based, you can get a Mac-based computer system. You can get something like an Arduino that isn't really it's a microcontroller, it's not really a computer system. You can get something like a Raspberry Pi, which is Linux-based, all depending on what kind of requirements that your computational needs for your project. And so that would be, that would be at this level, right? You don't really need to delve any more into that, right? If a Raspberry Pi satisfies your requirements for your computational system, you're done. You don't need to break that down anymore. But if you're designing, let's say, an attitude, direction, and control system, and you see what's on the market and you go like, all right, yeah, there are these different systems, but it doesn't really satisfy all the requirements that I have for this. Then you go, all right, do I want to design this myself, right? Do we want to make this in-house? and you go, all right, if we're going to be doing this, we're going to have these different subsystems, these different assemblies, and these assemblies are going to have these different components, right? And then what you start to do is once you have this component tree fully broken down, is you start to allocate functions to them. So you can say, all right, this subsystem right here, I'm just going to get the color for functions again. All right, I used green. All right, so for this function, so for this subsystem, we have F1. So this subsystem is responsible for performing function 1. And this subsystem, this assembly is responsible for performing function 2. So what you're going to be doing next is you're going to be doing the same thing that we did with the allocation of requirements to functions. Is what we're now going to do is we're going to take our components. Oop, that's still green. We're going to take our components and we're going to allocate our functions. So we're going to start allocating functions to components, right? So now we have a full traceability from our requirements. We know which components we're going to be using, or which components, assemblies, subsystems, systems, whatever we're going to be using. We know exactly what those systems, subsystems, assemblies, and components are supposed to perform, and we know exactly what requirements those functions must perform to, right? So now that we've done that, now that we've done that, and we've done our research and we know what components we want, we go on into, I think I used red for this. I'm just going to go all the way back up here. I used green, all right. Just to avoid redundancy, I'm just going to use purple. We go into the build section. So we have our list of functions, we have our components that we know that are going to perform these functions. Oh, actually, sorry, before we get into build, I completely forgot about the last half of the 2.5 design trees. So we have components, we have functions and behaviors. What's that other half? Now, that other half tree is, now that we have components and the systems, components, assemblies, subsystems, systems, now that we have them, these components, we call them A, B, and C. What we're going to start doing is just going to start, and they're performing functions. Yeah, put that in here. F1. Actually, let's not make these boxes. Performing F1, F2, and F3. What we're going to be start doing is we're going to say, okay, how are these different systems interconnected with one another? So this is the half design tree. And I say it's a half tree because it's not really a tree. It's more like a web. So the half design tree, the last half, which is, actually, I'm just going to give the name here. The internal component structure. All right, in this diagram, or these sets of diagrams, what you're going to be illustrating is the connections between different components, or actually, I'm just going to say connections. You're going to be illustrating the connections between different components, assemblies, subsystems, and systems. The interfaces and the item and logical flows. Now, what do I mean by that? So, the connections would be something as simple as, nope, not that one. There we go. The connections would be something as simple as A is connected to B, right? Now, you want to also say, all right, A is connected to B through an interface on A's side, so interface A, B, interface B, A, right? And they might be different. Now, an example interface would be something like a USB. So A is connected to B through USB. But you can also get into a little bit more detail here, right? You can say A is connected to B through USB over the serial 0 interface using software A.py, right? And the specific communication protocol that you're using between A and B, right? So we've established a connection, we've given the interface, and then what we're going to say is we've got something flowing between the two, right? These two systems are connected. What is going on within that connection, right? So this can be anything from power, or it could be data of whatever kind. This could be telemetry data, this could be positional data, this could be control data. Something is flowing, some data is flowing between A and B. If you're working with hydraulics, this could be different fluids. You know, something is flowing from A to B. So we also want to define, so in the interface we've defined how, in the interface and connection we've defined how and what systems are interfacing and how they're interfacing with one another. In the item and logic flows, we're illustrating what is actually flowing and what form or format that item or data flow is taking, right? So it could be you are sending, so let's go back to the satellite example. We could be sending health and state reports. So in that flow, you could be sending health and state reports from A to B. All right, they will be taking the they will be taking format A, and we're going to be encrypting these through encryption method B. So you have a format as well as what's actually flowing. Now, with these connections between your different systems, you can have multiple item flows going through the same interfaces, through the same connections on a system. So an example of that would be you have system A and then system B with some kind of interface, and a connection between them. Now let's say this is the USB interface. Now we know that they're sending serial data from A to B. We know they're also sending over the USB power from B. Sorry, I'm just going to put power. You don't need. So one thing that I will say is that you also, in addition to the item and logical flows and the format they take, you also want to specify the direction of that flow. Sometimes items will be bidirectional, so something like serial data between two different computer systems. There will be a lot of back and forth, so it's not just a one-way connection. In cases where it's something like power supply or you're sending water from A to B, or you are transporting rocks from A to B. It won't necessarily be bidirectional, it'll just be one-way connection. So you want to specify the direction of the flow in addition to what is actually flowing. So we have, so this is a good example of what kind of item flows you can make. So it can be bidirectional. So an item can have multiple things flowing through the same interface and connection. You can also have multiple connections between two systems. Oops, sorry. Through different interfaces. Now, a good example of this would be something like, I'm just going to say computer systems because they tend to have a lot of connections. You can have, let's say, your computer can be connected via USB to your mouse, or you can have your computer connected through USB to your separate, like let's say an RPi or a slaved computer device, or you can have it connected through HDMI. So you can have multiple. Oop, I don't want to put this in purple. You can have multiple systems connecting through the same interface, the same type of interface. You want to also, if that's the case, you want to specify, yeah, they're not actually using the same USB port. So this one's using USB 1, this one's using USB 2. So just keep that in mind. You can also have systems connected through the same interface with multiple logic flows. So it's very free-form in this sense of how these different systems are connected. So you have, right now you have, so at this point you should have different systems with different functions, with different connections, with item flows going through those connections to your different systems, each of which should be performing to specific specifications according to your requirements. So I'm just going to illustrate that here with your requirements. Right, and you can do this on multiple levels, right? So if you notice, the component tree hierarchy is very interconnected, right? All of these are comprised of one another and have interconnections to different systems. You're going to be going in this internal component diagram, or diagrams, I should say. You're going to be going up and down this tree quite a bit, right? So you can have an internal component diagram that works on the system level. So just the interconnection between the systems, where you'll have a lot of different connections between these systems, because in reality, you can also have it through their subsystems, which will have fewer connections, but you'll have a lot more different blocks connecting to one another. So an example of this would be so if A, B, and C were systems, you would have a lot of these different connections going through each of these with a ton of different interfaces and a lot of different logic flows, because you're not expanding it fully to show what kind of connections that you have. You can also look at it at the subsystem level, where you could have something like A, B, and C. Break down into A1, A2, and A3. So let's say this is A1, A2 to A3. All kind of under the blanket of A. And they have their own interconnections. B1 and B2. And so you have the connection between, the real connection between A and B is through A2 to B2. And you can break this down even further. So you can have internal component diagrams from the system level, from the subsystem level, on the assembly level, and on the component level. Now you'll notice that each of these kind of expand according to the component hierarchy that we mentioned earlier. So remember that component hierarchy we defined? So as it breaks down A, B, and C, A1, A2, A3, all of these, so we have A, B, and C, these are the biggest blocks on here. Then you have A1, A2, and A3, all within A, because that's the relationship, the hierarchy, the component hierarchy defined. And then B1 and B2, which are also within B, because that's the way that the component hierarchy was defined. So you can have all these different levels of looking at your project as a whole, and each of them will be useful in their own regards. If you're just trying to troubleshoot one specific aspect of your system, and say, like, let's say something weird is going on with this process, you know, okay, with this process, let's take a look at that function, right? You've got, in that function, we're doing this, this, and this. This is the process for that. These are the components that are allocated to that process. All right, then we're only really going to be looking at this subsystem, right? So you go to the subsystem diagram that's correlating to, and you go, okay, if we follow the logical path of that function, so going from A1 to A2 to A3, where are we getting the problems that we're seeing, right? So being able to look at your system from different levels, from high to the very lowest level, is helpful. Again, I will state that not all of this is necessary depending on your project. If you're working on something that's really, really big, like something like an aircraft with like 40 million screws and tons of different assemblies and tons of different electronics in it, you're going to want to be able to look at the system on all of these different levels, because sometimes you don't want to have any extraneous information that you're looking at, because if you looked at the entire system as a whole, it'd just be like you know, like these massive interconnected spider web of stuff, then you'll never be able to tell anything about the system. But if you know, all right, we know we're specifically looking at subsystem A, you know, components A, B, and C, you can narrow your focus down, and you can be able to refine that aspect of your design to a much higher degree. But if you're working on something like, let's say, a really simple Arduino project at home, you just want to have lights on the ceiling and stuff like that, you probably don't need to go into extremely detailed diagrams on how the system's going to work. I would say just at a system level, you want to understand it's going from the Arduino to the lights, this is the kind of code it's running, this is the interface, that sort of thing. Because that way you know the general flow of your system, you know generally what code is being run on it. It's a lot easier to troubleshoot and refine from that point of view. So don't make your job harder than it has to be. You definitely don't need to make all of the diagrams in the system. That being said, if you're working on a really big project, you probably will have to do all of this. It is really helpful for the design engineers to be able to look at and refine individual aspects of their system. So now that we've got these internal component diagrams, going back to the design process, now that we have these internal component diagrams, we have the component hierarchy, and we have the functional hierarchy, we move on towards everyone's most fun part, which is number 2, building, the next phase of the design process, build. Now, I won't actually go too much into detail on this. In fact, I'm just going to touch up briefly on the different aspects of building, because it's a very different beast of design, and it's typically tends to be very specific to what you're actually building. If it's electronics, then it's going to be going a lot more into interfaces and interconnectivity. If you're designing a more physical system, then it goes into the machining tolerances, and actual drawing specifications and how you're actually making these parts and what kind of materials you're using, etc., etc., etc. So I don't want to go too into the detail of how to build because it's very specific to whatever project you're working on. That being said, the build process, I'm just going to say you go through whatever build process that you need to do to build the component that you've described in your internal component diagrams, along the systems that you have researched and intend to apply. So with that being said, I'm just going to double check that I'm using the right colors here. Testing, I used purple. So then we move on to the third step of the design process, testing. So in this case, what you're going to be doing, hang on, let me just scroll down here. So what you're going to be doing in your testing is you're going to be testing everything that you've done up until this point. So you have this model, you have these components, you have these functions, you have these item flows and interactions, and what you're going to be doing is you have these requirements, most importantly the requirements. So what you're doing in testing, you are testing for requirements. Let me put this in blue. Let's make things colorful. You are testing to verify requirements, functions. It's a bit confusing that everything's. I'm going to put this in black. You are testing for requirements, functions, and connections. Now that you've built whatever system that you've done, that has to be in black. You want to make sure that that system is working the way you want it to do, the way you want it to. All right. So there are, I want to say, two different ways that you can test a system. Now, the way that I like to do it is you can do tiered testing or meticulous testing. Now, when it comes to tiered testing, say you have a design tree, or you have a set of functions and systems, or you have a set of systems, right? Let's go to the, actually, put this in red because this is going to be the component tree. You have some component tree, and you have some, you have some interconnections. I'm just going to try and loosely show what you kind of did in the interconnection, in the internal component diagrams, and you have some functions associated with these and some requirements. Now, what you're going to be doing is, I would say, you want to be able to first test functionality. Second, test requirements, because if you're not functioning or not performing the functions that you've described, you'll never meet requirements anyways. So in tiered testing, what you're going to be doing is you're going to be testing, from the bottom up, you're going to be testing through the tree, right? You're going to be testing this first, this second, this third, right? So you're going to say, all right, does this subsystem 1 perform its function, function 1? Or is my mouse showing up? Or, yeah. Does subsystem 1 perform its function? Does subsystem 2 perform its function? Then you go, okay, if you're given the green light on that, check, check. It's doing all its functions and item flows properly. Then you go, all right, let's go through up to the next system. All right, does subsystem 3 perform its function? Check, right? Is it sending out the proper signals? Is it sending out the proper formats, etc., etc.? So, and then you move on to the next allocation. So you're working up your way up through the tree in accordance to the system. You're testing one subsystem, the other subsystem, the other subsystem, right? The second way to do things, so the order in which you would do it if you were doing tiered testing would be 1, 2, 3, and then 4, 5, 6, and then you can test 7, right? You can test the entire thing, right? So you're testing the subsystem, the smallest components of subsystem 1, the next smallest components of subsystem 1, subsystem 1, the smallest components of subsystem 2, the next smallest components of subsystem 2, subsystem 2, and then on until you work up. You work up your way through the tree based on the systems that you're working with. So you go this first, this second, this third, right? Now in meticulous testing, I'm going to recreate this tree here. Now the advantages of this is you sorry, I'm going to go back to tiered testing for a little bit. The advantages of tiered testing, it allows you to quickly find errors within your system and isolate the errors to a system. What I mean by that is if you have an issue with a smaller component, you can fix that issue and then move on, and you're still working within the same subsystem. So if you test the entire subsystem, by that point, if you've done everything underneath it, it should be good, right? You should get a green light on your subsystem if you've done all the components, if you've tested and verified all the components and assemblies underneath it, right? So it's all its item flows are working, it's performing all its functions for all of the components and assemblies beneath subsystem 1. So when you test subsystem 1, it should work, right? You fixed all of those issues. But it can run into issues on very large projects, which is where meticulous testing comes into play. So sometimes if you're a test engineer, you will run into very large component trees, and you have a lot of different testing tests to go through, and only so much time in the day. And it takes 3 hours to set up a test, and you want to get through as many as possible. So sometimes you're going to do what's called meticulous testing. So meticulous testing, unlike tiered testing, which goes up the branches, or goes up and then over the branches of the tree, of the component tree, what you're going to be doing with meticulous testing is you're going to be going layer by layer. Oop, this is red. I want this to be black. You're going to go layer by layer by layer by layer, right? So system 1, subassembly 1, 2, or actually make this more easy. 1, 2, 3, and 4 all perform the same tests. You just set up the test once, do bang out 1, 2, 3, and 4. You go up to the next level, bang out 1, 2, 3, and 4. Or 5, 6, and 7, 8, 9, and then 10, the whole thing. So meticulous testing is optimizing for time. So, and I'm just going to make a note of that. If you've got a lot of different subsystems that you got to test, and all of them are using similar tests, or it takes a while to set up a test, then you are going to go through meticulous testing. Just set up the test once, and then bang out each and every system that you're going to be running on that test. And then you go to the next test, set up that test, bang out everything that's going to be on that test. Whereas with tiered, it's optimized for functionality. You can clearly understand where you're going to be running into issues with tiered testing. You're going to understand very quickly whether you're running into design issues with certain aspects of your components. If something's not, and you've got a very quick turnaround time for being able to redesign your system. So like, okay, we've got this issue, we've gone through, we know A, B, and C all work properly. It's just D that's not working properly within subsystem A. Subsystem 1. Okay, so then we just have to look at D, see if we can fix it, replace it, or if there's a design issue there, fix it, replace it, retest D. All right, it's performing. Then you go back up through the tree. So in that way, it's optimized towards functionality, and I find it works generally well with most projects. So typically, with whatever projects you're going to be working on, you're not going to be doing meticulous testing unless you're going to have to do 400 different tests a day. With tiered testing, so things like home projects, things like student projects or student team projects, or indie startup projects, you'll want to do tiered testing. You want to make sure that each level of functionality works first, then you move on. So that is the general gist of testing. Now, what I mentioned before, when you want to make informed design decisions, so I believe it was, we have a little bit up here. Here. Yeah, the research, testing, and experience. So the testing that goes with making your design decisions kinds of happens in tandem with your components. During the testing phase. During the testing phase of the design process, and that can happen kind of while you're making the design decisions. You say, all right, we know A and B. We're deciding between a field programmable like CPU, like a FPGA. Sorry, we're trying to use an FPGA or like a CPU, and we're not sure which one we want to go with. We've got these different models. We're going to test these two along our requirements and see which one works. Or you've built it already. You've made your design decisions. You've built it already, and you're going through testing, and you're going like, this CPU is having some issues. It's not meeting computation requirements. And we've looked through it, and it's not a software issue. It's a pure hardware issue, and which means we're probably going to have to switch models out. It might be time to revisit that design decision and go like, all right, let's look at these different variations and reintegrate with the design tree. So these internal component diagrams might change as the design process goes on. You go like, we have a different methodology for approaching this problem. We found we've optimized data pathways through the system. It's way better to go through directly from B to C than it is to go from C to B to A, or C to A to B. Or we found a much better interface that we're using. We found a much better algorithm for compression that we're using to make things faster, smarter, what have you, whatever you're doing. So as you're going through to the design process in your testing, you're going to be making changes to the internal component diagrams. You're going to be making changes, sometimes you're going to be making changes or additions to the component hierarchy. You're also going to be making changes to your functional hierarchy. So you go like, we forgot about that. We needed to add that. This function, actually through our research, we realized that this function breaks down even further into these different categories. Or most commonly, you will get requirements changes. So if you talk to your customer and you go like, we actually kind of want you to do this, this, and this, then you would go into and you change the requirements, see if how that changes your system design. So one thing I wanted to add to the function step of things is there's something you can do in addition to, other than simply describing the functions. Sometimes what you want to do is you have the functional hierarchy, right? And you've got its breakdown. But you don't really understand how each of these functions are performed. Now, one thing that you can do to help with that is you can start making activity or state diagrams for the system itself. Or just for that function specifically. So you say, okay, we have function 1. But what is actually going on in function 1? We know it breaks down into F1A and F1 or B and C, but we don't actually know what that function's actually doing. So what you can do is you can also create these diagrams alongside the functional hierarchy that kind of describe exactly how these system functions are being performed. So you can say this can be implemented with your MATLAB code or whatever. You can say like C plus B or C plus B equals X, right? And then say flow X down to B. X plus Y equals Z. Flow Z down to C. Right? You're just describing the activity and control flow of that function. So you say perform A, then go down to B. Then we have a conditional, perform C. I'm using official SysML notation. If you guys want to look up into that, that's a whole different thing. So this would be a merge node and whatnot. But look up activity diagrams and SysML notation. You can look at that. That's just the nomenclature for going through different activity diagrams, function diagrams, yada, yada, yada. So you'd have a decision node. So like if B, if A, then go to activity C. If not, then finish that activity. So you have a start node, goes to A, does some calculations of some kind, does some system interaction of some kind, goes to B. So you have different components associated with these. And you have, go away. And you have different requirements associated to these. So the components must be able to perform the functions, and the functions must satisfy the requirements. So you can go through these diagrams to explicitly detail what each function is actually doing and the process thereby it goes through each function. So, and you can look at this from a system, subsystem, assembly, and component level the same way that you do the ICDs. So the comparison for that would be if you take your ICDs and you go, okay, you have this sort of system interaction with this sort of interconnection between them. We have some sort of function flow and logic going through the A's function, which it then finishes, it finishes after it sends out information to B, or actually I'm going to switch things around to make things have things make a bit more sense. So function A's activity finishes when it sends out the required data or item flows to B, where now you have, so this is A. B. So A performs its function, it goes through its steps, it finishes when it sends out whatever information it has to be. Now you can have also some interactions and send stuff out to B through intermediary steps. Just no hard rules here. Sometimes you'll be communicating with other systems, waiting for other systems to respond back in the middle of your functions. So you'll have loops back. Oh, it shouldn't be in purple. So you have like waiting loops or stuff like that. Just in whatever way that's convenient to you to describe the functions and map the detail of that function in tandem with your internal component diagrams to get a full picture of the functional flow of information and resources throughout your system. Because then you can go, all right, I know this function has this requirement, and I know this function, now this function has this requirement. All right, given a certain circumstance, I can put that input data into this function and say, all right, does it meet that requirement? Yes, no, right? Okay, moving on. Yes, all right, moving on. Function 2, does it perform, let's roll those numbers through function 2. Does it perform its requirement? Nah, it does not. All right, then we go through that function and go, all right, with these component specs, what would need to change under this circumstance in order to perform our functions to those requirements? And that's pretty much what you're going to be doing throughout the design. You're going to be running into issues, and then you're going to just fix them one by one. And this goes back to the entire testing process with the meticulous testing. Is you're going to have these function breakdowns and internal component breakdowns, and you go like, all right, I know exactly what's going on in this component. Is it doing what I expect it to do each step of the way, right? And that's that. That's pretty much the entire design process. Just going up, back through it. I just want to make sure I'm using the right colors here. Even though I think we've run out of colors to use at this point, although I'm sure Microsoft has quite a few more. I didn't really want to use yellow because it's not as easy to see. So going back up here, just to recap. So in your design process, you're going to be making, I'm going to switch over to black here. You're going to be making your function trees, or sorry, first thing you're going to be doing is your requirements. Making sure they are single statements that are verifiable and are clear. Something that you can go back once you've started testing and you can say, have we done that? Yes or no, right? The second thing you're going to be doing is you're going to be going and defining functions. Hate discontinuity in color. You're going to be defining your functions, saying, okay, given our requirements, we know our system has to do, on a high level at least, A, B, and C. And then you're going to be breaking down those functions into like sub-functions, A, B, C, D. All right, in order to perform this, we need to be able to do this. And you just keep doing that until you can't do that anymore. All right, as things progress in your design, you may realize, oh, we missed one of these functions, or oh, this actually breaks down even further. And you can add that to the diagram, and you can, as things go on, you can refine and add more detail to each of these trees, right? So you've gotten your requirements, you've defined your functions, you've got your functional hierarchy. All right, now what you want to do is you want to start looking at your components, your systems, your subsystems, your assemblies, and your components. So you go, okay, all right, how, in order to perform these functions, we need A, we need B, we need C, we need D. All right, how do these components, systems, subsystems, assemblies, and components break down into one another? So you're going to be starting to look at the components tree. I say components. I really just should label this as systems, but for continuity, I'm just going to say components, because it's looking at the physical architecture of your system. So you've got your requirements, you've got your functions, you've got your components, you have allocated requirements to functions, and then you've allocated functions to components, assemblies, subsystems, and systems. Now what you want to do is you want to start looking at the internals. The internal connectivity between your components, assemblies, systems, subsystems, and how they interconnect with each other, what kind of interfaces they're using, what kind of items or data or whatever is flowing between your different systems, subsystems, assemblies, and components. So what's actually flowing and how are they connecting with each other? Right? Oop, that should be black. And then once you've got that down, what you're going to be doing is you're going to be defining, this doesn't necessarily need to happen last, you can kind of do this after functions. So this can kind of go into this space here or this space after here. You're going to be starting to look at the function breakdowns, the activity, the actual how are these functions are performed, right? You know how they're structured, what they're comprised of, and you want to work your way from the bottom up, right? Because if you start at the very high level, you're like, your very high level functions are going to be something around the order of, we need to be able to point the spacecraft, or we need to be able to point the space vehicle. And you go like, all right, well, there are a lot of different things, a lot of different functions that breaks down into, and the connections between those sub-functions are very complicated, and it's not very easy to define. But if you look at the very bottom level first, it's very easy to say, okay, in order for us to brake the system or brake the car, we need to engage brakes, all right? And how do we engage brakes? Well, we hit on the brake pedal, which sends transmission fluid from the braking system to the actuators on the brake discs. Those clamp down, which slows the car down, which also produces heat from the braking discs, and yada, yada, yada. So something like that you can fully define. I'm going to put this, as define function activities. Then you're going to build, after you've done all these steps in your design, you're going to build your design, and then once you've finished and building your design, your project will be very specific to what project you're working on. If you're working on something mechanical, you're going to be working with a lot of tolerancing and all of that, and diagrams and what kind of materials you're using, what kind of forms of materials you're using. Like, are we using aluminum? What kind of aluminum are we using? What kind of manufacturing methods are we using? A lot of different stuff with materials. If you're working with electricals, you're more concerned about interfaces, attenuation loss. You know, if you're working with cameras, that sort of thing. So it's very dependent on, building is very dependent on whatever project you're working on, and I don't have experience in everything. I in fact have a very limited experience, so I can't tell you everything there is to know about building things. And then once you've built your systems, you can start testing them. So you can start doing the tiered testing. So I'm going to write this down. So you can start doing tiered or meticulous, if it's a big project, testing, working with all of the aspects that you've generated in your design to make sure that each system, subsystem, component, and assembly is performing their functions as needed, and each of those functions is making sure that the requirements that are assigned to them are satisfied. All right, so once you've done that, if everything's given the green, you have a finished project. Congratulations. If you've run into issues when you're testing something, you go back to your design, apply some thought and say, all right, is this how, is the error occurring with how the systems are interconnected? Is the error occurring in what components I've selected? Is the error occurring because I'm missing a certain function? Identifying that error when you're testing, you've run into an error, identify where that error is coming from within your design, make the changes in order to satisfy your design, and then you move forward from that. Then you retest, see if it works. If it works, you move on. If it doesn't work, you keep changing aspects of the design until that works, and you move on, and then you have a finished project. So hopefully that goes through all the different aspects of project design in a very high level sense of what you need to do. Now, again, I'll go back to that initial preface that I made at the beginning of this video. Systems engineering and systems design is handled very differently from company to company and field to field. So be aware that changes may occur, and it's always best to conform to industry standards wherever you're working in. Now that being said, I will include a link down below to the NASA Systems Engineering Handbook. And they go over all the different deliverables and all the different documents and trade studies that you'll make through your research between different components, different models that you're using to test things, etc., etc. They go into all of that, all the different aspects of what you want to actually make as part of designing your system. So with that, I hope this video was informative. I hope you learned something a little bit about systems engineering and design. And I'll see you in the next video. All right, thanks.